In Chapter 6, we're going to talk about proof by contradiction, and that's the focus of Section 6.1. So we're actually going to start here with a proof by contradiction. And I want to talk through this proof and sort of talk about what are the things that are happening here, what makes this a proof by contradiction, and how that actually works. So again, we're going to start with this example. So it starts off, it says assume not. Right? So here I'm just really introducing the fact that I'm doing a proof by contradiction. So let me spell introducing correctly. Introducing that we're doing a contradiction. And we'll see some different ways that we can do that more explicitly. So I'm assuming that it's not true that if a, b are integers, then a squared minus 4b is not equal to 2. So for that to be not true, then my hypothesis has to be true, but my conclusion has to be false. So right, the negation of P implies Q is P and not Q. And we'll see this more in section 6.2. Then, now I've assumed this is equal to 2 as part of my proof by contradiction. So I am allowed to use that. Remember, usually we can't use our conclusion as part of our thing we're trying to show, because I'm just trying to show it. I don't know that it's true. But here I have assumed the negation of that, so I can use that. So I can move things around. A squared is equal to this. So a squared is 2 times something. So a squared is even. Right, so this is sort of my algebra step. But let's see where we're going to try to lead to. I get a squared is even. We've seen before that that means a is even. So I plug back in what a is. Now I know that a is 2m. I multiply that out, so that gives me again an even number. So I get 2 equals 4 times some stuff. So I divide both sides by 2 to get 2m squared times minus 2b equals 1. But then that tells me that 2 times this integer equals 1, which implies that 1 is even. At that point, you might be sort of sad, because what we did was we just sort of like, I think of this as breaking math. I just broke math. I said that, oh, we ended up proving something that was definitely not true. But when you're doing a proof by contradiction, that's really the goal, right? So we're going to get some contradiction, something that's definitely not true, right? So on one hand, we know 1 is not even. And now we just proved that 1 is even, which is not true. It can't be true that it's both even and not even, so that's our contradiction. Now we have to ask ourselves, why did we actually get a contradiction? Well, way up here, I assumed something that I wasn't sure if it was true or not. I assumed that the negation of my statement is false. So we get this contradiction, which means that the assumption must have been bad, because that assumption led us to break math. So it's not true that the negation was true. So that statement basically can't be false. Therefore, that statement has to be true. So I'm showing that if we assume our statement is false, we break math. Therefore, it must be true. And that's this general flavor of a proof by contradiction. We're going to assume the statement we want to show is false. We'll show that that leads to a contradiction or that leads to some issue. So our assumption must have been false. So it's false that it's false, therefore it must be true. And we'll see that on the later slides. Okay, so again, let's go ahead and break down this proof by contradiction. So I'm trying to prove some statement P. It doesn't necessarily have to be a conditional statement. Sometimes, right, my P will actually be some conditional. A implies B. Right, that could be its own little statement there. But I'm just trying to prove some statement P. So how a proof by contradiction works is I'm going to assume the negation of what I want to prove. So I'm going to assume not P. And then I want to get some contradiction. So I want to get something that's definitely false. And the contradictions, we're going to usually think about them in the form of something is true and its negation is true. So maybe we knew previously that 1 was not even. Now I proved that it is even, so it both can't be both even and not even, and that's where we get our contradiction. So we conclude, right, that it's impossible for our assumption to be true. So it's impossible for not P to be true. If it's impossible for the negation to be true, then that must mean that the original statement is true. So that's this flavor of a proof by contradiction. Assume the opposite, break math, get some sort of contradiction, conclude it can't be true, that P is false, therefore P must be true. Symbol-wise, sometimes once we get this contradiction, we just sort of stop in our proof, and we use this little symbol, which is like two arrows pointing at each other, to mean that we've gotten to some contradiction. But when you draw that, it actually looks like a line with an X on it. So you'll see that sometimes in handwritten proofs as we're sort of doing our scratch work. That means that we got a contradiction. So I can think of it as an arrow and an arrow sort of hitting into each other. All right, so let's actually do a proof by contradiction here. So the most famous proof by contradiction, the proof by contradiction that you almost always do first once you learn about this thing called proof by contradiction, is this proof that the square root of 2 is irrational. So in order to talk about that formally, we do need a definition of rational and irrational. We've talked about this a little bit before in the class, but I did go ahead and just copy that formal definition of rational into our slides here. So a real number is rational if x can be written as a over b for some a and b and z. And I always like to include that the b can't equal 0. Just so that when I'm going backwards, so if I have some number written as a over b, I know that it's rational. I want to make sure I'm not saying that infinity or some undefined concept is rational. And then it's irrational if it's not rational, so that it can't be written as a over b for any a or b in z. All right, so to show the number 2 is irrational, I'm going to use this proof by contradiction. So I'm going to assume the opposite and assume the negation. The opposite of being irrational, the negation of being irrational, is that it's rational. So I assume square root of 2 is rational. One other thing to notice here, right, is this statement is not an if-then. So it's not a conditional. So this is the first proof technique that we've seen that's going to allow us to prove statements that are not in this conditional format, this P implies Q format. So that's something that's also kind of interesting about this technique. Okay, assume it's rational. What does it mean that it's rational? We know that it can be written as some a over b, where a is in z, and we'll say both b and a is in z, and b is not equal to 0. Now I'm going to do one extra step here, and that is I'm going to assume that my fraction is in lowest terms. So assume that there's no common factors between a and b, so the GCD of a and b is 1. If it wasn't 1, you could just divide both of them by their GCD. So if not, we just divide by the GCD. So we reduce that fraction to lowest terms. Okay, so if square root of 2 can be written as a rational number, then it can be written as a fraction in lowest terms. So that's going to be our assumption. And now we're going to just do some algebra to this. So the first thing we're going to do is nobody likes fractions, so we're going to multiply everything across. Let me not go down too far there. So b times square root of 2 equals a. Nobody likes square roots, so I'm going to square both sides. So I get 2b squared equals a. Now I say, okay, well, a is equal to 2 times something. So thus, oh, sorry, I forgot to square the a here. So a squared is equal to 2 times something. So a squared is even. And we've seen that if a squared is even, then a is even. And you could go ahead and prove that as a lemma if you weren't convinced. So if a is even, a can be written as 2 times, I need a letter I haven't used before. So I've used a and b, so let me just use k here, where k is an integer. So then what do we get? 2b squared equals 2k, quantity squared. So 2b squared equals 4k squared. Divide by 2. So b squared is equal to 2k squared. All right, so what do we have now? Well, now I've got that b is equal to 2 times something, or b squared. So b squared is even. Thus, b is even. Okay, so what do I have? I had that a was even. Now I have that b is even. But I also assumed that the GCD of a and b was 1. Because any fraction can always be written as a fraction in lowest terms. So this gives a contradiction. Because I can't have that a is even and b is even where that fraction is in lowest terms. Right? A over b is in lowest terms. So why did I get that contradiction? What was the assumption that I made? The assumption that I made was that square root of 2 was rational. So that assumption must be false, so it must be true that its negation is true. So we have that square root of 2 is irrational. Right, this other thing up here, I did say assume here, but maybe I should have instead say where, because I'm not making a second assumption there. I'm actually changing the problem so that I do have that in lowest terms. Otherwise, it makes look like I've made 2 assumptions, and I'm not sure which assumption I'm sort of causing me trouble. But really, I only had to assume one thing here, which was that 2 was rational. Everything else came from that. That led me to break math, which means that my assumption must have been false. So we have that conclusion. So again, this is one of those most famous proof by contradictions. All right, let's do one more proof by contradiction in this section. We're going to prove that there are infinitely many primes. So this is actually sort of a neat proof, right? We know prime numbers are numbers that are only divisible by 1 in themselves. And it seems like, as numbers get bigger and bigger, there's just like more options of numbers that could devise them. So it seems like we could easily convince ourselves that it's possible that at some point we run out of primes, that we have some sort of largest prime. But it turns out that that's false. There are infinitely many primes, and we can prove that even without knowing what those prime numbers are. Right, so currently there is some largest known prime. I encourage you to look that up. It's kind of interesting. It changes every couple of months. They'll find a larger prime. So if anybody wants to fill that in here. There is some largest known prime, but we do know that there's actually infinitely many. So how would we go about proving that? Let's do our proof by contradiction. So I'm going to assume not. So I assume, and maybe I'll tell the reader here that I'm going to do a contradiction proof. So I'm going to say assume for sake of contradiction, so they know why I'm going to be assuming the opposite of what I'm trying to show. That there are finitely many primes. So then we can actually list out all of those primes because there's only finitely many. So I'm not going to list them out what they are, right, because it could be a really large number, but I can index them. So let P1, P2, P3 all the way up to some Pn be all the prime numbers. Right? What it means for there to be finitely many primes is that there's some n, which is the number of primes, so I can list up all of them up to that n. And now what I'm going to do is I'm going to think of a number which would have to be divisible by one of those primes. So I'm going to think of something bigger. So it's not one of the primes itself, but then it would have to either be prime, which would be bad because I already have all the primes, or not be prime, which means it has to be divisible by one of my primes. And we'll see that that's impossible. So let's consider P1 times P2 times P3 all the way up to Pn. So that number is divisible by every single one of my primes. And then I'm going to add 1. So this number can't be prime, right? This is larger than pk for all k equals 1 to n. It's larger than any one of my primes. So A is not prime itself. But if it's not prime itself, it must be divisible by some prime. So A must be divisible by some prime. It has to have some prime factorization. But if I consider A divided by some pk, that's going to equal P1 all the way down to Pn divided by pk plus 1 divided by pk. So that A divided by pk, we know that this is some integer. That's going to equal P1 all the way up to pk minus 1. I get rid of the pk, I kind of cancel that out, and then I have a pk plus 1 all the way up to Pn. So that's an integer. This is an integer. But then I have 1 over pk. Or I can say that 1 over pk is equal to this a over pk minus p1 all the way up to, there's actually this neat notation where you put the pk in there, but then you put a little hat on top of it. So that means we're going to remove that from its product. So that equals this, which is in Z, but that gives me that contradiction. Because I know that 1 over a natural number is never equal to an integer unless that pk is 1, but 1 is not a prime. So I got that contradiction because I have 1 over some number being an integer. Why did I get a contradiction? Way up here, I assumed that there are finitely many primes. So it's impossible that there are finitely many primes. So I can conclude there are infinitely many primes. This is really the word infinitely. I'm just very lazy at writing words. Infinitely many primes. So I would definitely encourage you to take some time, really internalize how this proof is working, right? Assume there's only finitely many primes. Multiply them all together to get this really huge number. Add 1. That can't be prime because it's bigger than all of the primes. I've assumed there's finitely many, which means it has to be divisible by something. But it can't be divisible by any of the primes because it's 1 more than a factor of that. So then we sort of get into this contradiction, so we couldn't have had all the primes to begin with. So take some time, think about how this proof works. It's sort of a really nice example of a proof. All right, so for the last thing in this section, I want you to think about how to prove the following statement, which says for every x in pi over 2 to pi, sine x minus cosine x is greater than or equal to 1. So there's a similar proof in the book for a similar statement where x is between 0 and pi over 2. So if you get stuck, you can look at that, and we'll talk through this proof in class.